Good morning, and welcome to this session, The Art of Java Type Patterns. What we're going to talk about is some interesting new features in terms of the Java language that we've seen over the last few releases and things that we may see over the next few releases. So to start with, let's just talk a little bit about modern Java. What we've seen for the last few years is a switch from the idea of feature-based releases to the idea of time-based releases. So rather than waiting 2, 3, or even 4 years between releases, we now have a release every 6 months. And I have to say that I think this is working really well. We've seen more features added to the Java platform over the last 4 years than we've seen in probably the previous 10 before that. So I think the architects of OpenJDK have done a fantastic job of enabling us to get more things into Java and addressing the needs that developers have. Now, one of the sort of bigger projects, which is part of the OpenJDK, is Project Amber. And this is more of a sort of an umbrella project rather than focusing on one specific thing. It focuses on a number of issues, and as I've put here, it explores and incubates smaller, productivity-oriented Java language features. And one of the other nice things about having a 6-month release cycle is it now also allows us to effectively have preview features and incubator modules. That means that we can add a feature, but we still have the opportunity to get feedback and let people play around with it. And then if they think that there should be some changes, they can send feedback, and we can actually incorporate that before it becomes a final thing. And we'll see how that's actually happened as we go through here. So this is another really good way of actually doing that. So pattern matching in Java. Okay, we have this library, java.util.regex. Okay, and we can use that. We can create a pattern. We can compile that to recognize A followed by 0 or more characters followed by B. And then we can create a matcher on a particular string, and we can then match against that and get a Boolean to say whether we matched it or not. Okay, or we could do it in a single line. Wonderful. Okay, well, we're not going to talk about that at all. That's it. Finish with that. What we're actually going to talk about is pattern matching at the language level. So what do we mean by that? What are the fundamentals of pattern matching? Well, this is actually a technique that's been used for a long time. You can actually go all the way back to the 1960s, and if you look at languages like Haskell, if you look at languages like Awk, anybody here used Awk? Okay, good. Reasonable number of people put their hands up. Excellent. Awk is a wonderful tool. It's used in those types of languages. But what actually do we mean by a pattern in this sense? It's not like the regular expression type pattern that we were looking at before. So a pattern consists of 2 things. We have on the left-hand side a match predicate. And essentially what we're doing here is we're determining whether the pattern matches a given target. And that's really a sort of very formal way of simply saying we have an if statement. So we look at something and we say, if this is true, then we want to do something. And the thing that we want to do is on the right-hand side, which means that we have a pattern variable or variables, could be more than one. And in terms of using that, if the test on the left-hand side, the pattern predicate or match predicate that we're looking for matches, then we will conditionally extract something based on the pattern on the left-hand side and use that as a target that we can use in the rest of our code. So that's the sort of rather formal definition of what we're dealing with, but we'll see how that works as we go through. Now, there are a number of different pattern types. We have a constant pattern. This is already in use in Java. If we look at the switch statement, we have case labels, and those are constants. You know, you can match case 1, case 2, and so on. We know about that already, so that's a fairly standard thing. If we match on 1 or we match on 2, we can do something with it. We also have the idea of a type pattern. That's really what we're going to talk a lot about in the rest of the presentation. So we match on a type in Java, a class, and then we do something with it. There are some other pattern types that we can use, and we'll again explore some of these as we go through. The idea of deconstruction pattern, where we can take the thing that we're matching against and potentially extract something from it rather than just referencing it as a variable. Then we have the idea of a var pattern, which uses type inference in the same way that JDK 10 introduced the var to the Java language. We can make use of that within a type pattern and effectively match anything. Again, we'll talk about that as we go through. And then the last one we're going to talk about in this presentation is the any pattern, an underscore. So that matches anything in the same way that a var would, but in this case, it binds to nothing. And again, so it's an unused pattern variable. We'll see an example of that later on. There is one more type of pattern that we could talk about, which is a method pattern, but because I don't have any examples of that in terms of changes to the Java language, I've left that out. Right, before we actually get into the details of pattern matching, there's a couple of other things that have been added to the Java language in the last couple of years that we need to talk about because of the relevance of type patterns to those features. First of those is around switch expressions. Now, we've seen in, I think it was JDK, let me have to think about this, was it JDK 12 or JDK, no, it was JDK 12, where we introduced the idea of a switch expression. Previously, we've had switch statements in Java, and we know all about those. We brought those in from the C programming language, so we understood the syntax of those. The problem with having a switch statement is that it executes a set of instructions, but it doesn't generate a result. And that leads to a situation where, combined with other aspects of the syntax of a switch statement, mean that you can have potentially error-prone code. The fact that every case statement or case block needs to be separated, the fact that you have to remember to put a break statement in your case block, otherwise it will fall through into the next one. So again, little show of hands here. Who has ever forgotten to put a break statement in? Yeah, exactly. Yes, we all know the problem of that. Even if you've got your IDE that's helping you, it's actually quite easy to do that. I know I've certainly done it a number of times. And even the scoping of local variables is sometimes not quite intuitive. So if we look at a simple example of the idea of a switch statement, this is the kind of thing that we very frequently do. We're switching on one variable, day, and we want to assign a value to another variable, number of letters. And so we do this in the traditional way where we have case Monday, case Friday, case Sunday, number of letters equals 6, remember to put our break in, and off we go. We can do that for all the different days of the week. But as I say, either we could forget to put the break statement in, or we could forget to assign a value to number of letters, and because it's an instance variable, it gets set to 0 by default, so the compiler won't find that, and we could end up with a situation where we've got a bug that might be difficult to find. So in JDK 12, we got the idea of a switch expression. Now what we can do is we can execute the code in our switch, but we return a result. And we can assign that to number of letters. Because we only do that once, we've eliminated the problem of having to remember to do it in every place. The compiler can check that we are returning a value or throwing an exception from every set of cases, so it's a compile time check rather than leaving it to runtime. In terms of the syntax, it is simpler. We have less lines of code. One of the reasons we have less lines of code is that the developers of this particular feature, they looked around and they found this incredibly powerful feature that nobody had noticed before. It's called a comma-separated list. And so what we could do is we could actually put case Monday, comma, Friday, comma, Sunday. Who'd have thought it would take 25 years to figure out that we could do that? It's not really rocket science, but anyway. So then we borrowed the lambda operator, the arrow, and on the right-hand side of that operator is the value that we return from the switch expression. This is all good, or we throw an illegal state exception. The wonderful thing about this is it's less lines of code, but we lose none of the readability. Okay, so the other thing that we have to remember about this is that switch expressions must be complete and exhaustive. And I'll come back and talk about that a little bit later when we talk about some of the other type pattern matching. The other thing we can talk about before we get into the details of the type patterns is algebraic data types in Java. And again, if we look at the way that Java worked before. We have the idea of object-oriented programming. We have classes. We can encapsulate data, state, behavior, and so on. And we end up with something like this, a point class, which is basically a tuple. We have two values, double x, double y, but in order to do that, we need to provide references to the instance variables. We need a constructor, which takes two variables, x and y. We then need to assign the values of those to the instance variables, plus we need accessor methods that will return the value of x and return the value of y. 14 lines of code just to create a tuple. Now, I've always thought that wouldn't it be nice if we actually had a tuple class in the Java libraries? And I did mention this to Brian Gertz, and he said, yes, we could give you a tuple. But the problem is then you'd want a triple, then you want a quadruple, and where do we stop? So to get around that problem, what they've done is introduce in JDK 14 records. Great. Now what we can do is we can simply say record point, specify that the values we want to store in there are double x and double y, and that's all we have to do. The compiler will fill in all of the details for us, eliminate all of that boilerplate code that we had on the previous slide. 14 lines of code becomes 1 line of code. Excellent. Now, we can deal with records in terms of treating them as just a special form of class in the same way that an enumeration is a special form of class. Because we can do that, we can make them generic, so we can store anything using a generic type parameter and do that. The other thing we can do is we can add more information to the record itself. If we wanted to, we can include additional static instance variables. The only instance variables that we can include that are dynamic must be specified in the record definition, but if we want static ones, we can do that. And we can add additional methods. In this case, I want to have a circle, so I can add a method that determines the area. All good. A couple of other things that we need to understand about records. First thing is that the base class of all records is java.lang.record, which means that a record cannot inherit from another class. We have single inheritance in Java, so we can't inherit from another class as well. However, we can implement as many interfaces as we want to. Again, it's just a normal, or just a special form of class. Records also are implicitly final, meaning that you cannot extend them further. It's designed to be a simple data type, so we don't want to have complexities involved in terms of subclassing them. You can add the final modifier to a record if you really want to, but it's not necessary. And the other thing we need to understand is that the records do not follow the Java bean pattern. This was, a slightly contentious decision that rather than using the bean pattern of saying that the accessor methods would be called get, followed by the name of the variable, get x, get y, they would just use the name of the variable. So we have method x, method y. Sometimes that can be a little bit problematic because if you're using a framework which is expecting the bean pattern in terms of accessing the things that you want to store data in, then you have a little bit of a problem because it's not going to use get x and get y. However, there is a little trick to get around that, which is simply call your variable get x or get y. And then it will actually produce the method called get x and get y. It's a little bit if you must. The other thing we need to know about is Java inheritance. So again, object-oriented language, we have the idea of inheritance in that. So we have a class called shape, which has 3 subclasses, triangle, square, and pentagon. We cannot control who can subclass from shape unless we make it final, in which case nobody can subclass from it. And as we'll see when we get into the type pattern part, we'll see that there are situations where it would be really useful to have a closed set in terms of the classes involved. And to get around that, we now have the idea of sealed classes, also introduced in JDK 15. And what we do now is we say, add a modifier to the definition of our class. We say public sealed class shape. And we add a permits clause that says there are 3 subclasses allowed from that, triangle, square, and pentagon. If somebody comes along and says, oh, I like your shape class, I want to subclass that into a circle, it won't work. The compiler will reject it because it's not listed in the permits clause of that class definition. The other thing that we have to know about is that for sealed classes, all of the subclasses of a sealed class must explicitly state their inheritance capabilities. And there are 3 ways of doing that. So the first is that we can continue to have a sealed class, and we then specify another permits clause with further subclasses. In the case of our example there, we can say sealed class triangle, and it permits equilateral and isosceles as other subclasses. Second thing we could do in terms of inheritance capabilities is we could make the class final, so there will be no further subclassing of that. And then the last thing that we can do is to use the hyphenated contextual keyword non-hyphen sealed. And we can say, add that as a modifier, and that way now anybody can inherit from Pentagon. So it's now opened up, and there is no restrictions on that. Right, so now let's get into that pattern matching bit. What are the current pattern matching capabilities we have in Java? Well, first of those is around the instance of operator. And this is code, again, that we've had right from the very beginning of Java. Because it's object-oriented, we have the idea of polymorphism. We can view an object as being a number of different types based on the interfaces it implements, based on the hierarchy of the type definition. So if I pass an object reference to a method and I want to determine what specific type it is, I use instanceof. And I do this. I say if obj instance of string, then I want to do something with it. And in order to use that, the very first thing I have to do is to do an explicit cast with an assignment. I must say that I create a new variable called s of type string, and then I'll assign that to the value of obj, but casting it using the string cast there, which is sort of really just redundant code, isn't it? Because if we pass the test, then the ability to do this cast is going to happen anyway, and most likely we're going to want to use that reference. So it's just, why do we have to do it? And the answer is now we don't have to do it, because what we can do from JDK 14 is use pattern matching for instance of. Now, if you remember at the beginning, I talked about the idea of a pattern being a predicate, which is where we're looking for a pattern to match. In this case, the pattern that we're matching is if obj is an instance of string. So that's our pattern part, the predicate. And then the pattern variable is the thing that we will use to reference that in the code further on. So we give it just the variable s, which we now know will be of type string. So that eliminates the explicit cast that we had before, eliminates a little bit of boilerplate code, and doesn't lose any of the readability. Now what we can do is we can say, okay, if obj instance of string s, if we pass that test, the body of the true branch of the if statement, the reference to s will be valid as a string. We can call the methods on that and determine the length of the string. In the false branch, clearly we haven't matched that pattern, the predicate, and so we don't have a valid reference to s, so we couldn't use s in the false branch there. We can take this a little bit further, and we can say if obj instance of string s, and then use an and operator, and check to see if the length is greater than 0. This will work quite nicely because we know that when we use the and operator, we will always evaluate the left-hand side of the operator, and only if that evaluates to true will we evaluate the right-hand side of the operator. If it evaluates to true, we know that we have a string, so s is valid as a reference. We can use it on the right-hand side of the operator. We can test the length and determine if it's greater than 0. That will work. If we were trying to use or in that case, that wouldn't work because, again, we know that in the case of the or operator, we will always evaluate the left-hand side of the operator, but only if that evaluates to false will we evaluate the right-hand side. If it evaluates to false, we don't have a string, so the scope of s is not going to be valid on the right-hand side. We can't call length on that, then the compiler will reject it. The scoping of variables is sometimes a little sort of maybe counterintuitive, and you have to think about it a little bit more carefully. We might have a situation where we invert the test. So if we say if not O instance of string S, meaning that we want to look at if it's not a string, then we're going to return. But that means that from that point onwards, we know we do actually have an object which is a string, and we have a reference to S. We can print out the length. We could then have several hundred lines of code, and if we wanted to print out the value of the length of the string further on, then we would still be able to do that. So the scope of S extends all the way down until we return from that method. Which brings us to the idea of how scoping works with our binding variables. We use what's called flow scoping. Now, if you look at the way that local variables are scoped, we understand that, because scoping for local variables is from where that local variable is defined until the end of the block of code in which it is defined. So whether it's a loop, whether it's a method, whether it's just a block of code. Locals are also subject to the idea of definite assignment, meaning that you have to make sure that a value is assigned to a local variable. Otherwise, the compiler will reject it. Unlike with instance variables, where the compiler will give a default value to an instance field, in the case of local variables, you must make sure it has a value assigned to it. So from the point of view of the binding variables that we use with our pattern matching, what we're dealing with here is that they are also subject to definite assignment. A value has to be assigned to it in order for it to be used, which is very logical. But what that means is that the scope of the binding variable is, as I put here, the set of places in the program where it would be definitely assigned. And that means that if we look at the simple example previously, where we do if obj instance of S, the only place where that has validity is in the true branch of the if statement, meaning that that's the scope where it's valid. Same thing with the more complex example where we invert the test. The validity of where S has a definite assignment is after we've returned, because we've gone through the inverted test and we've returned because it's not a string. So this is what flow scoping is all about. And you have to remember that the flow scoping is not the same as it is for local variables. And a good example of that is that we can do this if we want to. And we wouldn't be able to do this if we were just using the same scoping as we had for local variables. We can say if O instance of integer num, we'll use num as the binding variable, then we can use that in the block of code. Else if O instance of float, and you reuse num, same thing, if it's a long, we can reuse num, because we know that the scope of each of those references to num is only going to be in the block of code that's associated with the true branch. And that way, we don't have to then provide different variable names for each of the situations that we have there. So that just kind of tidies things up a little bit and just makes our life as developers a bit easier. Now, here's an interesting one for you. Right, so if I create a piece of code like this, so object S equals new instance of object, and then I say if S instance of string S, print out the length of the string is s.length, else print out no string. Who thinks that this code will compile? Okay. Who thinks it won't compile? Who doesn't know? Okay. All right, and just one last one. Who thinks both it will compile and it won't compile? No. Well, the answer is yes, it both will compile and won't compile. How is this possible? How can we have quantum superposition in a piece of code? This is, finite deterministic automata. It must be either one or the other. And this really confused me, because if you put this into your IDE, if you put it into a piece of code and you compile it with Java-C, it will be rejected. You will get rejection because the variable S is already used and you can't reuse it for string S. Very logical. Except that if you put it into jshell, you get this. It will actually work in jshell. So it will quite happily look at that and treat S as a variable, even though S has been used before. I have no idea how this works, because I thought jshell was built on top of Java-C. It used the Java compiler underneath. But apparently not in this case. So anyway, I just thought that would be an interesting thing to include. Next kind of pattern matching to look at is pattern matching for switch, We saw earlier on that we now have the idea of switch expressions as well as switch statements. And one of the limitations of using the idea of switch is that you can only switch on certain things. You can switch on integral values, numbers, you can switch on strings, and you can switch on enumerations. What we now have is the idea of expanding that so that we can switch on type patterns as well. And what we can see is an example of that here, where we've got a method called typeTester. We pass in a reference of type object, which is going to be some specific subclass that we want to deal with, and then we can switch on that. And then we have a set of cases that deal with different types. First of those is quite important because we have the ability to have a case specifically for null. This is something we haven't had in the past in terms of switch statements, but now with pattern matching for switch, we can explicitly add a label for a null. Because a null is a null is a null, we obviously don't have a binding variable because it doesn't make any sense. So simply we'd have case null. If it's a null, we can print out we've got a null type. Then we can deal with specific types, and we can say in the case of a string, we have a binding variable which we'll call s. On the right-hand side of the operator, we will be able to print out what the value of s is. If we have a color, again, we provide a binding variable c. We can use that, and we can reference a method from the color class and print out the RGB values. Now, primitives are not types in the sense of classes in Java. Obviously, we have wrapper classes for them, but if you just look at a primitive like int, we can't use that as a case. But we can use a case for an array of ints. An array of ints actually is a type in Java, so we can say case int brackets and give it a binding variable ia, and then we can print out the length of the array for that particular value. And then, of course, we've got a default there just to print out whatever the thing is that we've got in the case of something else. So null, as I said, null is a little bit special and is a little bit more complicated than you might think. If you have a case statement at the moment and you pass in, you're dealing with a string, for example, and you want to do a case on that and you have different values. If you pass in a string which has a null reference, then what you're going to get is a null pointer exception. Very logical, that's the way things work in Java. So what we can now do is we can have case null, and that can be used in all switch statements and switch expressions, meaning you can use, it's expanded what you can do in the switch statement as well as the expression. The important thing, though, is if you don't include that, what will effectively happen is the compiler will add that for you to throw a null pointer exception. Again, if we look at the example we had before, we haven't included, in this example, a specific null case label. So what will happen is the compiler will put that in for us. So if we've got a null, it will throw a new null pointer exception, and we will get the same behavior that we would have before. So it allows us to do that without explicitly stating it, but it will add it in for us. But what that does mean is that we can also deal with it explicitly. So we can put it at the top where we do it ourselves, and we can we can test against null, but we could also include it in the default statement and say, in the case of null or default, meaning anything other than the things that we've specified above, then we print out we've got bad input, and we don't have to throw a null pointer exception. So we can handle it in a slightly different way if we want to. Again, gives us more flexibility in terms of what we actually want to do with this. So the other thing that we need to be aware of is the idea of completeness. If I take this example here, I've got my typeTester class again, and I pass in an object O. What I'm doing here is I'm saying switch on O, and if it's a string, print out what the string is. If it's an integer object, print out the value of the integer. That's all good, except what happens if O is actually a float? Well, we could say, well, because it doesn't match on either string or integer, we don't do anything with it, and we just continue with the rest of the code. But that doesn't really make much sense, and the decision was made that it's actually better to handle all possible situations And if you don't handle all possible situations, the compiler will give you an error. The logical thing to solve that problem is to simply add a default case. Now what we do is we say, okay, if it's a string, we print out the string. If it's an integer, we print out the value. Anything else, we just print out a message which says some other type. So now we have got completeness. Any type that we pass to that will be handled by the switch statement there. That doesn't mean you do need a default case. You can, in the case of using our sealed classes, we could take the example we had before of our shape, and we could say, okay, let's pass in a shape to our type tester, and now we'll have a switch statement on that, and we'll deal with the case of triangle, case of square, case of pentagon, and the case of shape, but we know that that's a sealed class, so we have covered all possible eventualities in terms of a shape. There are no other classes that could exist that would deal with that. Even if we deal with the idea of we had the further subclassing of triangle, because somebody brought this up, I must remember to say it, even if we have the idea of triangle where we've subclassed it into isosceles and equilateral, because we have a class for triangle, and triangle is the superclass of isosceles and equilateral, it will match on that, and so we have covered the ability to deal with all possible types of a shape. Even if we don't deal with all the specific subtypes, we have dealt with all possibilities. Now, what we can also do is we can include the idea of guarded patterns. And this kind of comes back to what we saw earlier with the idea of the instance of pattern matching, where we're able to say, if obj is an instance of string s and s.length is greater than 0, then we can do something with that. We can also apply that within the switch statement. So we can, or the switch pattern matching. So what we can do here is we can say, okay, switch on shape, and the first thing we'll do is we'll say, if it's a triangle, add a guard to that. So we'll use the AND operator, and we'll say, if it is a triangle T, and T.area is greater than 25, we know that the scope of T will work, because if we match on a triangle, we have the binding variable T, that will work, all good, we print out it's a big triangle. If we don't have an area that's greater than 25, the next thing that we go to is a case of triangle. So the triangle has an area that's less than 25, then we can catch that with the case triangle on its own, print out it's a small triangle. And then again, we deal with square, we deal with pentagon, we deal with shape, meaning that we've got, again, completeness because we've dealt with all possible situations, even the guarded one or the unguarded triangle. And the syntax for that is simply that you do primary pattern, use the AND operator, and then you have the conditional AND expression. Now, that's the way it works in JDK 18. JEP 4.27 was only announced last week, and that's going to be included in JDK 19, which is an update to pattern matching for the switch, and that changes things slightly, only very slightly. Rather than using the AND operator, they've decided to use the keyword when. So now we say case triangle T when T.area is greater than 25, then we print out it's a big triangle, and we just do it that way. So it's a small change, but again, this is where we see the idea of preview features allowing changes to be made before it becomes final. Pattern dominance is the other thing that we need to talk about, because we need to make sure that the order in which we put our cases doesn't hide things. If we change the order in terms of the shape tester, or the type tester with shape, if I put the shape first, of course, shape is the superclass of triangle, square, and pentagon, so it would match against any shape. And that way, we would never get to the idea of a triangle, a square, or a pentagon specific case. We would always say it's a shape, and that's it. The compiler will therefore reject that and will say, hang on, shape will always match first, so triangle, square, pentagon classes are unreachable. That is not right. So your dominance is that shape dominates the lower cases, and because that's the case, we need to put it at the bottom to make sure that it only matches if we've got something that is specifically a shape. That also applies when we use a guarded pattern, because if we change the order of the cases that we had in the earlier example, and we say case triangle T, print out a small triangle, Then we have triangle t when t.area is greater than 25. Obviously, if it's triangle, we'll always match on the first case of just being a triangle. We'll never do the guarded situation, and therefore the compiler will complain about that, and it will say, okay, triangle will match before the triangle with a guard, so we need to change the order of that to prevent the dominance of the triangle on its own. That gets a little bit more sort of subtle when we deal with guards, and we could do something like this. Now, I don't know why you would do this, but you could do it. And if you said case triangle t when true, and you can do that because, of course, the right-hand side is just an evaluation of a Boolean. So if you simply say true, it's always going to be the case. That would also fail because we would never get to the point where we have triangle on its own. So we've effectively got two cases that do the same thing. One is hiding the other, so the compiler will reject that, saying that the guarded pattern is dominating the unguarded pattern. The good thing is that the compiler will point all this out for you, so you don't have to worry about dealing with it yourself. You'll just go, okay, yeah, compiler understands that. So basically the situation that you have to have is a compile time error for a label in a switch block to be dominated by an earlier label in that switch block. That's the rule that you have to follow, and that's what the compiler will enforce. What are we going to see in the future for pattern matching? Well, obviously the JDK 19 stuff I just talked about, where we're going to use when rather than and, is slightly in the future, but at least it's been announced. There are some other things we can do. So pattern matching instance of and records. What can we do now? Well, if we've got our record that we defined earlier, just a point with an x and a y, what we could do is something like this. We could have a method which takes an object reference, and we say if O instance of point, and then use a binding variable p, so that we can use that p within the body of the true branch of the if statement. Then we can extract the value of x, we can extract the value of y, and we can calculate the length of the hypotenuse. Now, okay, I don't actually have to assign them to variables. I could have done it in a single line, but you get the point. Excuse the pun. Yeah, you get the point, which is that we have to extract the variables from the point. So why don't we do a little bit better than that? Why don't we say, let's use pattern matching for records. So this is another JEP that is proposed. We're not quite sure when it's going to be included yet. But the idea is that since a record is just a special form of class, why shouldn't we be able to use a deconstruction pattern on this? And now what we should be able to do is say, okay, if O instance of, and we'll say point, but we'll define it as a record within the pattern binding variable. So we say point double x, double y, then what we can simply do is say print out the hypotenuse and do the math.square root x squared plus y squared. And what we're doing is we're extracting deconstructing the record by defining what it's got in it, get the values out of it, and off you go. Let's make that a little bit more complicated because patterns are also composable. Take our record called point, which has x and y. Let's introduce a numeration color, which has got red, green, blue. Then we'll create two more records. One's a colored point, which has a point and a color. And then we'll create a color rectangle, which has two color points, top left, bottom right. And we'll say it implements a new class shape just because we need it to do something like that. It's not quite the same as the shape I showed you before, but it's an interface that I've just created. So now we could have the idea of a method which takes a shape as a parameter, and because it's an interface, we can have different things that implement it. And we say if s instance of color rectangle, and because that's a record, we can then specify the values that we've got. So color point top left, color point bottom right. And if we want to print out the color on the top left point, then we simply do print line top left dot c. Good. Okay, except that we know that color point is also a record. We could expand that. And so we could say s instance of color rectangle color point, and because it's a record, we can say point p color c and color point br. Then we just print out c, which gives us the color of the top right point. So now we're decomposing or deconstructing twice because we've got records in there. But of course, point P is a record as well, so why not expand that out? And we could say color rectangle, color point, point double X, double Y, color C, color point BR, print out X. All very good. But we can actually go further with this. Eventually, we can get this to really look good. So there's patterns and local variable type inference. Local variable type inference introduced in JDK 10. var operator. Now we don't have to worry about what the types of things are. Why not use that in our deconstruction pattern? So now what we'll do is say, rather than having to specify all those complicated types, we'll simply say color point, point, var x, var y, var c, var br, and then all we do is reference x. And then the last thing I want to sort of mention here is the idea of an any pattern match. So this is where I'm kind of going off the reservation a bit because this hasn't been proposed as a particular feature in Java, but I think it would be a good thing to do. So it's kind of related to another earlier JEP, which was lambda leftovers. And if you think back to JDK 9, you may be aware that the underscore, single underscore, was turned into a keyword, meaning you couldn't use it as a variable name. Anybody here use an underscore as a variable name? No, good. Well, a couple of people. Okay, probably not the best one, but even if you don't worry about that, you can still use 2 or more underscores as a variable name in Java. But anyway, so the idea with that was with lambda expressions, if there was a parameter in your lambda expression that you didn't use in the body of the lambda expression, you could simply ignore it, if you like, by using an underscore. And we could do the same thing with our pattern matching. So now what we can do is we say S instance of color rectangle, color point, point, var x, which is the one that we're actually interested in, but the other variables we don't care about. So they match against anything, but they don't bind. So that's the important thing. We just ignore them, and that way we've got no interest in them, so we'll just ignore them, reference x. Tidies it up, makes it a little easier to read. Probably got, have I got, yeah, I'm thinking I'm missing a bracket there. Last thing as well is pattern matching for arrays. Same idea, deconstruction pattern, same idea as a record where we can extract values from a record. How about if we can extract values from an array? What we could do is we could say if O instance of string array, and we'll give it a binding variable SA, and we'll test that the length is greater than or equal to 2. Then we can manually extract the values from that array by saying string S1 is SA reference 0, SA1, assign that to a different variable, print out the things. Why not simply say, okay, let's have instance of string array, we can match on that, and then we'll define the binding variables as string S1, string S2, and we could do that, and then we can say string or print out S1 plus S2 and avoid the problem of having to do the manual extraction. That was going to be included in JEP 405, but for whatever reason, the developers seem to have decided that's not going to make it into the pattern matching for records, which is what it was also included in. So just to summarize then, pattern matching, I think, is a powerful set of language features, language constructs. It's definitely there to simplify a number of tasks that we have. A lot of what Project Amber is simplifying things and eliminating a lot of the boilerplate code that we have. More declarative, more understanding exactly what's going on there. Also has the potential for better optimization, enhanced performance, sort of at the compiler level, we might be able to do some interesting things there. Some features already included. We've seen pattern matching, for instance, of pattern matching for switch, and we'll see pattern matching for records in the future and things like that. More to come. And we may see even more in the future. So there's some interesting stuff going on there. And my one marketing slide here, because I work for Azul, we do builds of OpenJDK. They're free. If you want to have a look at our website, you can find them there. End of marketing message. So thank you very much for listening. I do have about 5 minutes, so if anybody does have any questions, it might be a little bit difficult, but if anybody's got a question, put your hand up and try and shout. Okay, not seeing any questions. Oh, there's one right at the back there, is there? Why would you use this instead of regular polymorphism?
Yeah, why would you check
Well, you see, because the problem is if you use regular polymorphism, if you're passing in an object which is of type shape, then you can't treat it as a triangle unless you know that it's a triangle and you've assigned it to a triangle reference, because you can't call the specific methods of a triangle unless you know it's a triangle. So if you pass it in a shape, you have to treat it as a specific subclass in order to use it as that specific subclass. I don't know if that actually answers your question. Maybe come up and talk to me if that's not the answer you were expecting. OK, so I think that's it. If anybody does have any questions, please feel free to come and chat to me.